All right. Today we're going to look at creating a custom branch growth solver using VEX inside of Houdini. So let's get going and start from the top. All right. So first we have the line sub. This line sub is creating the main branch or the main trunk of the structure, if you will. Then we run it through a resample sub just to resample the line. This UV texture sub creates UVs along the length of the curve going from 0 to 1 in the U value. So we can see that here. If we look in the geometry spreadsheet, you can see point 0 has a U value, has a UV value of 0 and a value of 1 on the last point. So it's creating a nice attribute that interpolates nicely from 0 to 1 going along the length of the curve for us. And we're keeping that so that we can use it later on as a p-scale. And we'll see how we use that later on in the setup. This attribute VOP is just using noise to create some noise to break our curve up so that it's not so straight. Right? And if we jump into the attribute VOP, we can see that we're just using an anti-alias noise, and we are multiplying that by a ramp and adding it to the position of the curve, and that creates the deformation, this noise, and we can use this ramp to further adjust the deformation of the curve. All right, here now is where some of the interesting stuff really starts to happen. So this branch over here, this node setup over here, is creating the points from which our branches will grow. So we scatter some points onto our initial curve. So I just templated the curve here so that we can see it in the background to see what we're talking about. So we scatter some points along this curve. And as you can see right now, we're scattering a total of 10 points. And the amount of points we scatter here is equivalent to the amount of branches that we will grow. So we're scattering 10 points, so we'll grow 10 branches because the branches will grow from these points that we are scattering here. All right. And then we color these points black. Now, I want you to remember that these points are black because that will become important later on. Remember, these points initially start out as being black, which is a color value of 000, R0, B0, RGB 0 in all the channels. Then we do this sort. Now let's look at why we have this sort node here. So if we look at the initial curve, we can see that the point numbering goes from 0, 1, 2, 3, as we'd expect, sequentially, right? But when we scatter, we can see that this changes. So now our first point is 0.1, second one is 0.9, then 8, and it's sort of messed up, right? So we want to sort it so that we can have 0.0 here, 0.1 here, 0.2. So we sort based on the Y. All right, so we just do a sort by Y, point sort, and now we can see that we get it how we want it with 0.0, 1, 2, exactly how we would want it. All right. This branch here, let's look at this branch right here. Before we jump into the solver sub, let's look at this branch right here. So we have it's also coming off of the main curve, just in case. So we have a carve sub here, and the mode is by default usually set to cut, but here we set the mode to extract. So let's look at the difference. If we have it set to cut, it's like we're growing the curve, right? Turn off the template. So it's like we're growing the curve, we're growing along the length of the curve, and we're growing the curve itself, all right? But when we have it set to extract, what's happening is that we extract a point, and then it's like we're moving that point along the curve. So now let me retemplate this curve, and we can see that we're extracting a point and moving it along this curve, which is really cool that we can do all of this within one node. All right, so I love the carve sub. The carve sub is awesome. All right, so let's look at this attribute wrangle node that we have here, which is simply, we can even replace this wrangle node just to make it more clear. Let's replace that node and add a color and change it to it's already points, and let's make it red. All right, so if we look, we can see that it's 1 in the CDR, 0 in G and B. So let's look at this. So now this point is red. This is important. Remember that these scattered points that we will grow branches from are black by default. So 0 in all color channel, right? And this point now that's running along our curve, it's red, right? This is deliberate. So before we jump into the solver sub, let's explain what it's going to do. So let's template these scattered points so we can see it better. This point that's moving along the curve with its red color, what will essentially happen inside the solver sub is that as it moves past each of these points, it will transfer its red color onto these points. Essentially, some people call this like an infection system. Like as it passes each point, it infects them with its color value, essentially. So we'll be just using a simple attribute transfer to transfer the color from the red point, as it passes these points, it will transfer its red value onto each of these points. The reason why we're doing this inside of a solver SOP, in case you didn't know, what a solver does is it does its current operations based on what happened on the previous frame. That's essentially what a solver does. What happened on the previous frame, it has memory of that. And whatever it's doing on the current frame, it's doing it based on the result that happened on the previous frame. So inside the solver sock, remember we're bringing in this single point that's moving along the curve. Let's untemplate these points. So the single point that's moving along the curve, where's that? Here. So it's moving along the curve. We're bringing that into the solver sock on the second input, and the scattered points that will actually be the growth position of our branches is going in on the first input. Now again, let's dive into the solver sock. So we have the attribute transfer. So the single point is coming into point input 2. So we're getting it from input 2, and we're transferring its CD, its color, onto our scattered points. Let's refresh this. So here are scattered points, and we're transferring that color value. So if we run the timeline, we can see that color value is being transferred to those points. And notice it's persistent, meaning here's our point up here, but these points down here still retain the color that was transferred to them from the point all the way up here. It still remember them, even though if we look at the distance value, it's very small. It's a small distance threshold. So if we weren't doing this inside of a solver sock, these points would only be red when this point is close to them, right? So once a point is no longer close to them, they would just turn back black again. So because we don't want that, we want to persist this red color. That's why we're doing this inside of a solver sock. So it remembers that on the previous frame, this was red, so I'm going to keep it red. Right, so that's why we're doing this inside of a solver sock. Now, if we look at this attribute wrangle, what we're doing here is we're creating what's called an ad hoc group, which is essentially a group that we create on the fly, and we're creating it within the group parameter here, just for use within this node. So this group is saying if a points, and notice we're running over points, so it's saying if a point color value red is equal to 1, that's when we will run this code. So only if the points color red value is equal to 1, that's the only time we'll run the code that's in this node. What we're doing here is we're creating a minimum value and a maximum value. The minimum value is 0, the maximum is 1, and we are creating this attribute called growval. This attribute is being created on our scattered points, and essentially when it's created here, you can think of it as having a value of 0. And what we're saying is we're clamping it between the min and max that we created up here, which is 0 and 1, remember, but we're updating this grow value as the simulation runs. So what we're saying is the grow value, which remember, initially it initializes to 0. So when it's first created, it's 0. And we're saying that grow value, which is 0 plus 0.01 as the simulation runs. So once a point has its red value become 1, this code runs, and we're saying create a grow value attribute, and as the simulation run, add 0.01 to it. So it will start at 0, and as the simulation runs, it will add 0.01 to this value until it reaches 1, because remember, we're clamping it at a maximum of 1, so it won't go past that. So let's take a look and see how this works. Looking at the animation here, let's untemplate the curve. Let's isolate this grow attribute in our geometry spreadsheet so you can see here. So again, by default, it initializes to 0. Currently, all our points are still black, so it initializes this grow value to 0. Now let's move the simulation forward and see what happens. So boom, this point becomes red, and now you can see the grow value is starting to count up. So it goes and it's counting, and you can see as it goes, it's updating for, so once a point becomes red, it gets a grow value, and that grow value starts counting up. So you can see that happening here until we get to the last point. And notice they're all clamped at 1. This is the value that we'll use to interpolate between so that we can grow curves from this point position out to some random point position out here to create the branches. So let's look at how that happens in the next couple of wrangles. So this wrangle here is just setting up the P scale. So we are using this UV value that we created up here from this UV texture, and we're using that to fit between these values. Very small values, 0.08, because it's a very small seed, 0.08 to 0.02. And the reason why we have the bigger value here and the smaller value at the end is because it's a branch, so it's thicker at the connection point and thinner at the root, at the tip, sorry, thinner at the tip and thicker at the connection point. So we want the thicker values here and the thinner value there. So all we're doing is creating this p-scale value and fitting it. Remember, it's a value that goes between 0 and 1. That's the UV value that we created up here. It goes between, take this out. So yeah, so you can see here it goes between 0 and 1, which is what we're doing here. We're remapping that. So 0 to 1, and we're remapping it between 0.08 and 0.002. So 0.008 and 0.002. All right. The next attribute wrangle now is where we create the actual branches that grow out here. So don't be turned off by this code that you see here. All pretty simple and easily explained, and I'm going to run through the whole code. First, let me change the background to dark so that we can see what's happening better. So here we go. What's happening within this wrangle? How are we growing these branches? Everything is taking place within a for loop. So this for loop is running over each point, and we're in the detail context because we're creating geometry. So here we don't have access to things like add pt num and so forth. So we're running over each point. This I variable essentially represents the current point number that we're running over. This essentially represents add pt num, the current point that we're running over. That's this endpoints function here is bringing in all the points of the geometry, right? From input 0, which is the first input on the wrangle. It's bringing in all the points of the geometry, and we're saying if I, which is initialized to 0, is less than the total number of points coming in, because this returns an integer number with the total number of points that the geometry has. We're saying if I is less than that, which as long as the geometry doesn't have 0 points at the moment, I is definitely less than that because I is 0, then we want to increment this I value as the for loop runs. So as I increment, it becomes the point number of the current point that the loop is operating on. And here now we're just bringing in a few attributes. So we're bringing in the grow val attribute. Remember, that value is what we created within the solver, which is that value that we'll use to interpolate between these points. All right, so we're bringing in that grow val attribute, and we're also bringing in the color. The reason why we're bringing in color is because we're going to use it in this if statement to know essentially when a point is active, because a point is only active, if I should turn this back to light mode, currently we can, when a point is black, we can consider it as being inactive. It only becomes active once it becomes red. As the simulation runs and it becomes red, that's when the point essentially becomes active. All right, so in this case, the color value is what's telling us when a point is actually active. So in this wrangle, that's why we're bringing in the color value, the color attribute, because we will use it to essentially tell us when a point is active. We're also bringing in the p-scale, which we will use to add scale attributes along our newly created branches. So we're bringing in that p-scale value. Now let's look at this if statement. All right, so remember, this if statement is essentially checking whether the point is active. Remember, a point is active when it becomes red. So essentially we are saying if the color R value is equal to 1, so if red is equal to 1, which means the point is red, then we run this code. So we're essentially saying if the point, so we could essentially change this value to active, and then we could change this to active, or we could say leave this as call, and then we could say active, we'd say int active equals call dot r. All right, and then we could change this whole thing here to active, which would essentially get us the same result. We change this to a float because it's a float. So there we go. All that caution is gone. And we're still getting the exact same result as before. So we can essentially look at this value as telling us when a point is active. So once a point becomes red, right, it's active. Code within this if statement will run. So what's the code within this if statement? What's going on here? First, we create this point pos vector attribute, or vector variable, I should say. And because these are not attributes, they're actually variables, just variables that hold data at the moment. Because notice we don't have the at sign in front of them. Like if you say at v, right, that's when it becomes an attribute. But in this context here, how we have it, they're really just variables holding data. So we create this vector point pos variable, which currently has nothing. It's just an empty variable, empty vector variable. And then we also have this vector variable here that's bringing in the position value of each point. So let's take a look at that. So each point, we're bringing in the position value of each of these points, right? Because remember that the I variable represents the current point which we're operating on. P is the position attribute, and we're bringing that in using the point function, storing it in this variable. Because remember, as I said before, we're going to create a point at each of these point locations, right? So we're going to create a point at each of these point locations. So that's why we're bringing in the point position for each of the points so that we can know that location to create our initial points. Here, we're just initializing some random values because remember I said if I show the points here, these points out here are basically the random points that we are going to create to interpolate between, to draw these lines between, all right? These values that I'm creating here are just some random values. You can find better ways to figure out values. These are just random values that I created manually to place points, right? So I'll show you how that works in this part of the code down here in a little bit, but essentially that's what these values are. There's random values that we'll use later to create these points out here, all right? So that's what's going on here. Now, notice there's a nested if statement. So we have an if statement within an if statement. So nested if statements. Yes, we can do that. All right. So this if statement now, this one is interesting because what this one is doing, it's the deciding factor as to whether we'll have a point on the right side, as to whether one of these random points will be created on the right side or it will be created on the left side. And the way it's doing that is using this modulo condition here. So remember that every time we see this I variable, remember that what it represents is the current point number, which this for loop, remember everything is still happening inside this for loop. So this I variable represents a current point number that this for loop is running over. This modulo operator returns the remainder of a division, meaning let's say this I value currently represents, let's say the value is 2 for this I value. We're saying 2 divided by 2. The remainder of 2 divided by 2 is 0. So essentially what we're saying, if the calculation from this is the same as 0, run this code in here. Else, if it's not 0, then run this code here. So if I becomes 1, right? If I is 1, what will happen is we're saying 1 divided by 2. The remainder of that is 1. Okay, so this value will be 1, and so what will happen is that we'll run this code in the else statement because it's not equal to 0. The reason why I'm using 2 is this is basically saying if the point number is an even point number, meaning 2, 4, 6, 8, if it's an even point number, run this code. If it's an odd point number, 1, 3, 5, 7, run this code. Right? So that's how I am determining whether a point is on the right side or on the left side. So if the point is an even point, right? What happens is that it runs this code, and here you can see now where we're using these values, x1, z1. So this random position vector, we're saying set it to make its x value be whatever this x1 variable is. Its y value, again, is just this manual arbitrary number that I typed in that I thought looks good. If I should type in a bigger number here, we can see these points get raised or dropped in this case. Right, they go down. If we type a number, we can see they go up. Right, so this is just manual values that I thought looks good, and it's the same for here. I can change these values as well if I feel like it. They can do that, but don't think that looks good. So change it back to this. These are manual values that I entered. So this is the x value for points on this side, the x, y, and z values. All right. Now remember this empty position, this empty vector variable that we created up here. So the reason why I created this empty vector variable up here is because remember, we're always only running over one point at a time. Okay, so I want to store the position value that one point should get. I want to store it in this variable, right? But remember, we can have either a position for even points or a position for odd numbered points, right? So two different choices based on whatever this if statement spits out. So we're saying that if it's an even number of points, set this variable, all right? So we're resetting this variable essentially, not redefining it because it's already initialized here, but we're now changing the value of that variable essentially from being nothing to, if the point is an even numbered point, change that position variable to be this value here, right? So now let's discuss what this value here is. This is a lerp function. So if I should pull up Google, good friend Google, and type in lerp VEX Houdini dots. And look at this verb vex function. When working with vex, the documentation is your best friend, hands down, right? I live in the documentation. So you come in, you look at this verb function, you say, okay, what does it do? It performs a linear interpolation between values. So it has a different kinds of functions here, because VEX has this thing called function overloading, which we can get into in a more specialized VEX course, which I definitely plan to do soon. So if we look at this, the float version of this function, it takes value 1 and value 2 and an amount. So value 1, so it will interpolate between these values. It will interpolate between value 1 and value 2, and it will interpolate between them using whatever value is in the amount section here. All right, so let's look at how this works in our code. So let's look at this alert value. Let's space it to give it some space so we can see better. All right, let's give it some space around it. So we have this alert value. The current, so we're alerting between, this is value 1, the current point position, which remember we brought in up here when we, so each point position for each point. So whatever point this code is currently running over, this current point pos represents the location of whatever point we're currently running over. All right, so this is value 1. All of this is value 2. All right, so what this is saying is the current point pos, so the current point position. So again, just remember that this is the current point position of what, if we're currently running over this point, it's right here, right? And we're saying that position plus whatever we just created in this random position, which again is one of these points out here. So if we are running over this point, this random position that we generated here in this vector represents this point. So if we're running over this point, the random pos represents this point. And then so we're saying from this point plus whatever the random pos is at a point there. So from here to here. If we didn't do this addition, let's look at what happened if we did not do this addition. If we just said use the random position value, you can see that this wouldn't work quite so well, because what happened is that we're now saying the random position is whatever was generated here, but do it from the origin. So we're starting from 0 from the origin and then going to whatever position value was generated here in random pos. So that doesn't work quite as well. We want the position to be relative to the point position, to each point's position. So that's why we need to do this addition, because this addition brings us to the location of the point. So from 0 to the location of this point, and then we want to now also add the random position that was generated here to that point, which now gets us like over here for this. So if we're running over this point, it gets us here. If we're running over this point here, it gets us here. If we're running over this point, it gets us here, right? So hopefully that makes sense. If it doesn't, leave some comments. I'll do a much clearer explanation of that using maybe drawings or something. There are lots of tutorials you can find on the web showing you how these vector stuff works, but essentially that's what's happening. So we need to do that addition here, and then this now is the amount value. So remember the parameters, that the arguments that our alert function takes. It takes value 1, it takes value 2, and it takes the amount. So we're using, so here now is where we're using this grow val. So in case you're wondering why this grow val was created within this solver, remember we created this ages ago within the solver, right? The grow value which updates as the solver runs from 0 to 1. Right, so now we are able to use that within this wrangle, which is generating our branches. We're able to use it within this lerp function. So we're lerping between the point position, right, of whatever current point we're running over. We're lerping between that and this new random point position that we generated using this here. So let's look at what happens when we do that. Let's turn off the line. Just look at the points. Let's look at what happens with the points. So there, turn this off. So the white points are the newly generated points. All right, so let's look at how they interpolate. Well, here we go. The point becomes red, does that. So those white points are the points that are being interpolated by this grow value. So interpolating from the current point position of whatever point we're operating on to that new random location. You can see that happening beautifully here. Then, so that's all that's happening within this if statement here. So this if else statement. So now we're outside of this if else statement. So now we're back into this if statement, right? And what we're doing here, so remember this if statement that we're now back into is the one that is running only if our point is active. And remember, our point is only active if its color value is red. So now this bit of code down here, this code does nothing without these, right? But essentially, it does something, but you won't see it until I activate these code down here. So what this is doing, it's creating an empty primitive Yeah, an empty polyline primitive, which is essentially a polygon curve, right? So it's creating that empty geometry, and we're adding these points. So we're creating the points which you're seeing here, these white points, which are interpolated points. I love seeing these interpolate between the points. It's nice to look at. So then now, here is where we're creating the lines, because the geometry needs vertices for the actual geometry to be created. So we are creating the prim. So if we should take a look again at these functions, the add prim, add point, and the add vertex function, let's once again pull up our documentation, right? And look at those add prim 2D, right? So add prim. So here you see it adds a primitive to the geometry, and it takes the geo handle, which again can be 0 to represent the first input. So it takes that, and it also takes the type. Now you can see, you can come down here to see the values that type can be. So type can be poly, which is a closed polygon, or polyline, which is an open polygon, which is what we want, or you can look at the rest here to determine. I truly only mostly use either polyline or poly. So, and you can take a look at the add point and add vertex on your own time, but it's essentially, but definitely check out the documentation for all of these VEX functions. All right. So with this add prim, so we now have primitive, and we now have the points. Now we need the vertices to connect them to create the actual geometry. So we need two vertices. So we need a vertex at the, let's come here. We're going to need a vertex at each of these points. And then we're also going to need a vertex out here at these randomly newly generated points. So we need two vertices. That's why we have these, we're generating these two vertices here. And that now gives us the line. And the line is created as the, between these points. So when the points are being interpolated, right? When the points are being interpolated, we're getting these lines, which is really neat and really cool to generate these simple branching structures. There are many ways how we could do this. We could make this code more complex, do more things, but this is essentially a neat, simple way how you can do stuff like this, and you can extend this to your heart's content. This is a really cool thing that VEX can do in a simple way, in my opinion. Yeah, I like it. So here now, this compile block, we put this for each block into this compile block just to make it a bit more efficient, because all of these nodes here are compilable, meaning are multi-threaded. All right, so we're in this for each loop, we're just running over each of these branches. Right, so what we're doing is we, notice that each of them only have 2 points, so we resample them. Right, so let's look at one. So we resample it, right? And then if we look at the point numbering, right? Point numbering is good. We didn't even need the sort, right? And then we're adding the UV texture. Now again, we're doing the same thing with the UV texture to create the UV values going from 0 to 1 along the length of the spline. This time we're using arc length spline. Not really sure why I chose that option there, but it works well. Here, as you can see, we're getting the value from 0 to 1 in our U, which is good, which is what we want. And again, we're going to use that for p-scale values, remember? Okay, so this attribute VOP, again, we're adding noise. So it's pretty similar to the first attribute VOP that we had here, that we used to add noise to the main curve. So here we're just adding some noise to each of these newly created branches. Right? You can take these setup further, and we're doing that for each of these curves. So you can see we have some randomness there, not all just straight lines. And then we're deleting any attributes that we don't need. For example, the color, we're done with it, so we don't need it anymore. So we get rid of it. It's more efficient to work this way. You delete attributes once you're done with them and don't need them anymore. Here, I use color just to turn this red so we can see it better on screen. Actually, we don't need it. Yeah, and for the sweep, we are just sweeping tubes along these curves, which gives us this growing structure. Okay, so hopefully, and then we can do a subdivide to get this even a little bit nicer. So hopefully this tutorial was clear as to how we can use VEX to do these kind of stuff, these kind of building our own custom solvers and such. VEX is really cool for doing things like these, and I will do a more foundational VEX series where I explain not just about VEX, but how to think in terms of coding when you're doing stuff like this for motion design or VFX or whatever the purpose is that you're using Houdini for. If you're struggling to think in terms of VEX, we will talk about treating VEX like a second language and understanding how to think in terms of coding as you develop tools and build assets within Houdini. Yeah, so hopefully you find this helpful, and as your journey with Houdini continues, hopefully I can post things on this channel that helps you with that journey. You can also request stuff in the comments, definitely looking out. And yeah, if this helps you, like and subscribe for sure. Encourage me to do more stuff, and more stuff is coming your way, definitely. So thanks for tuning in. It's your boy Trill, out.